Okay, so hi everyone. Thank you for joining this seminar. We are happy to host Dr. Eric Bergman. Eric completed his PhD in electrical engineering at Tel Aviv University in 2017, followed by a postdoctoral position at Brillouin University. And since 2018, he's been working at the research group of Professor Andrea Aliu. I hope I'm pronouncing his name correctly. Anu, okay. At the Advanced Science Research Center, the City University of New York. So thank you for coming, Eric, and please, the floor is yours.
Okay, can you see the presentation?
Yeah.
Okay. So again, thank you for the invitation and the opportunity to present my research. As I was introduced, my name is Eric Bergman. I am with the CUNY Advanced Science Research Center. And today, I would like to tell you about some of the hidden gems that marine engineers may not be aware of in their daily work. As you could already see from the title, I'm going to discuss light and sound, the two most widely encountered phenomena in marine information science and technology. The ocean soundscape is a mixture of different sounds that originate from natural processes or human activities. Long-distance underwater communication almost exclusively relies on transmission and reception of acoustic signals. Sound echo is also the basis for subsea navigation and seismic imaging. Despite the water's low transparency, light has many applications in sea exploration, such as lidar bathymetry, algal detection, broadband communication, and photography. When talking about light and sound, one should be reminded that the laser interferometry is in fact the most sensitive method known to mankind for measuring mechanical displacement. The LIGO observatory is capable of detecting strains of 10 to the minus 21, which is a displacement of 1 attometer along its kilometer-long arm. Absolutely amazing. So I say, put nothing in the ocean except optical sensors. You probably ask yourselves what this t-shirt has to do with anything. Well, it's actually quite amusing. When I was a young boy, I had this t-shirt that said, put nothing in the ocean except yourself. I wanted to show this slogan to you and paraphrase it. I tried searching the internet, but came up empty. Can you guess why I could not find the picture of this t-shirt online? I'm sure you would agree that this is because back then there were no broadband communication networks and no cloud storage that allow you to upload enormous amounts of data in a split second. Which brings us to a quick detour to discuss optical communication. Later in the presentation, I will show you how we can benefit from existing photonic fabrication processes and infrastructures to design our sensors and systems for marine applications. But first, let's do a brief overview of the role of photonics in enabling information and communication technologies. While information storage and logical processing are dominated by electronics, photons are the carrier of choice for information exchange between distant nodes of the network. When it comes to optical communication, two principal technological marvels stand out. The first one is the optical fiber. It has extremely low losses. It is as thin as a human hair and very cheap. It forms the backbone of optical networks, both inland and across oceans. This image is taken from a New York Times article about the deployment of fiber optic submarine cables. They ironically allegorize that the data is not in the cloud, as one might think, but it's rather in the ocean. The joke is actually on them, since optical fibers don't store data, but rather carry it from one place to another at the speed of light. To keep up with the exponentially growing demand for data, the total length of the deployed fibers has already surpassed 5 billion kilometers. The second technological marvel is integrated photonics, which enables high-speed optical communication at the rack, the board, and even the chip levels. The transmission density, much like everything in the exponential age, is also growing exponentially. Optical transceivers of hundreds of gigabits per second and millimetric sizes are already commercially available. but the data traffic still grows faster. However, just adding more infrastructure is probably the worst scale-up approach. Multiplexing is. Let us now take a brief look at the two principal multiplexing architectures that give pushback on the optical transport capacity crunch. The first one is multi-core fibers and multi-mode fibers, with which I worked intensively during my graduate studies. These fibers support large number of spatial channels and come in all shapes and sizes, practically allowing the degrees of freedom needed to design the communication link according to desired specification. This may include crosstalk, intermodal and polarization dispersion, mechanical properties, etc. These techniques, more widely known as space division multiplexing, already some years ago were shown to transmit petabits of information over a single strand of fiber. And they continue to push forward. Just recently, a fiber with 228 spatial channels was fabricated and evaluated for its transmission properties. Another principal multiplexing architecture is wavelength division multiplexing. The principle is quite simple. Several optical carriers, each carrying its own data stream, are combined at the transmitting end, send down a single fiber, and the receiver to split them apart. So the objective is to squeeze as many channels as possible into the transmission window of the systems. To give you some feeling for the numbers involved, here's an example of our recent work, which was done in collaboration with GAWBS Semiconductors here at Migdal Emek, where we demonstrated maximally flat WDM filters with narrow channel spacing of 70 GHz and strong out-of-band rejection. Of course, there are some details to this, but the most important message to us at this point is that this high spectral efficiency system was realized in a 1 square centimeter silicon photonic integrated circuits, using almost entirely standard fabrication protocols. While doing a dry run, I noticed that this slide also seems to suffer from capacity crunch. Sorry about that. By now, you already ask yourselves, why should marine engineers care about telecom technology? In my view, it is the same as asking why climb Mount Everest. The simple answer is because it's there. What I mean is that the optical fibers and integrated circuits fabrication technologies are mature. The equipment, laser detectors, amplifiers, modulators, filters are commercially available. And in some cases, we can also use the telecommunication infrastructures that are already deployed. You are all familiar with the traditional tools you routinely use in marine research. And I don't need to tell you how expensive the installation and maintenance of these systems are. I want to show you how photonics-based tools can supplement existing marine technologies and probably replace them altogether eventually. Monitoring of critical infrastructures, environmental monitoring, and sonic surveillance can be done with fiber optic cables. Those can provide much better coverage, resolution, and sensitivity. They can also provide access to new information, which can be obtained by any alternative means. The installation and maintenance costs can definitely be lower. And the photonic devices having smaller form factors can be mounted on mini ROVs or integrated into submarine cables and data centers. So if to summarize the many motivation slides in 2 bullets, first, we want to develop novel sensors and systems for marine research and monitoring. And to achieve that, we prefer to use existing photonic technology infrastructures or with as little modifications as possible. By now, you must have forgotten the title, but it includes a hint on the mechanisms that can provide unique handles on the challenges we wish to address. That is the interaction of light and sound. Let's start with the interaction between guided optical waves and an external disturbance, which modifies the optical properties of the medium. Please note that our discussion will not be limited to mechanical motion. We will also see examples of static deformations. A good place to start would be introducing the fiber Bragg rating. These are laser-inscribed periodic variations of the refractive index in the fiber core, which selectively reflect a particular wavelength known as the Bragg wavelength, and it depends on the effective index and the grating period. The width of this reflection peak depends on the index modulation depth, its profile, and the grating length. Let's see what happens to the reflection of an FBG when it deforms. When the grating experiences strain or temperature change, its period as well as the effective index change. As a result, the center frequency of the FBG reflection shifts linearly with strain or temperature change. This simple principle forms the basis for a wide range of useful devices. In this work, we used an FBG bonded to a composite plate to detect a surface acoustic wave packet, which originated from a nearby pencil lead break. This is a standard calibration procedure for acoustic emission sensors. Using a standard optical test bench, we were able to measure nanostrain amplitudes at frequencies of hundreds of kilohertz. Some of the most sensitive hydrophones also employ fiber Bragg ratings, both in passive interferometer configurations and in fiber laser cavities. In another work, we used an integrated diffuse Bragg rating as a compact surface acoustic wave receiver. And here I show you a design of an integrated optical accelerometer, which is realized on a silicon photonic platform. It comprises a Bragg rating etched in a suspended waveguide structure, which also effectively acts as a spring connected to a proof mass. As a result of acceleration along the sensing axis, mechanical strain is generated in the waveguide, which consequently shifts the Bragg wavelengths. To summarize this slide, the Bragg rating is indeed a very useful sensing element in fibers and integrated devices. The current technology also enables multiplexing hundreds of Bragg ratings in a single strand of telecommunication fiber. However, this reduces the spectral efficiency of the telecom link. And since no one is going to pull the plug on Facebook or Twitter so we can do research, we need another sensing mechanism that couples mechanical disturbance to light. Fortunately, we also have Rayleigh scattering, which accounts for most of the attenuation in optical fibers. But as the saying goes, one man's noise is another man's signal. Let's start with the physics of Rayleigh scattering. Let's consider the electric sphere placed in a constant electric field. The induced dipole moment is proportional to the sphere volume and depends on its dielectric constant. If placed in an oscillating field, having the wavelengths much larger than the sphere radius, it will scatter light with the total scattering cross-section proportional to the square of the sphere volume and inversely proportional to the force power of the wavelengths. Rayleigh scattering from air molecules is what gives the atmosphere its blue color. In a similar manner, the nanometric density and Doppler fluctuations within the fiber core give rise to Rayleigh or dipole scattering of the propagating light. However, a standard single-mode fiber captures only a small fraction of scattered angles, which amounts to a total of -72 dB per meter, which means that less than 1/10 of a millionth of the power is scattered from every meter of the fiber, which is not much, but this is what we have to work with. In order to use it as a distributed sensing mechanism, we are interested in measuring the Rayleigh spectrum of each resolution cell of length L, which is a fiber-unique information-rich signature. Clearly, the reflection from each individual scatter cannot be resolved, and what we essentially measure is a random phasor sums, whose intensity follow the Rayleigh distribution. So what will happen when we apply tension to the fiber? That stretched section of the fiber will manifest the same spectral signature, only shifted by some delta lambda. And similarly to the Bragg reflection that we just discussed, This wavelength shift is proportional to the applied strain or temperature change with the exact same proportion coefficient. Therefore, we may refer to it as a nature-made chaotic grating. These signatures remain unchanged for years. Similar to radars, the localization can be achieved by either pulsing the probing light or scanning of the probing optical frequency, each with this.
What P stands for?
Sorry?
What P stands for?
P.
1 minus PE. What is PE? Epsilon, I believe it's the strain. What is
yes,
PE?
epsilon is the strain. PE is the strain optic coefficient. One is the change, the actual elongation of the grating, and PE is the strain optic coefficient, which is the change in the refractive index due to
as a function of strain. Okay, thank you.
Some strategies for enhancing the performance of the sensors can also be considered. For example, rapid strain field changes can be monitored by tuning the probe laser to the linear slope of the FBG spectrum. When the fiber is stretched or compressed, the spectrum shifts to the right or left. This way, the dynamic change in the strain field is converted into the intensity change of the reflected probe. Need to keep in mind that the strain dynamic range of this method is limited by the spectral span of the slope. Another sensitivity enhancement method, also routinely used in radars, is pulse compression. Instead of a single pulse, a coded waveform is sent down the fiber. The reflected signal then becomes a weighted sum of delayed version of the system pulse response, where the weights are the code elements. Following detection, the signal is digitally correlated with a reference code. As a result, the effective response of the system is eventually governed by the metrics of the correlation function, such as the compression ratio and the peak to side lobe ratio. The signal to noise ratio typically improves with the square root of the compression ratio. Here you see the results of our laser engine experiment, where we used the 1.2 kilometer long waveform, and following processing, we're able to resolve reflections which were a few tens of centimeters apart. Here I show you a conceptual graph which demonstrates the trade-off between the resolution and scan rate of fiber sensors, which rely on elastic light scattering mechanisms. Green means good for telecom. Red means practically unsuitable. For distributed acoustic sensing applications, for example, we do not need fast acquisition. Sorry?
Sorry, please unmute the microphone. Gil? Toda, Gil.
For distributed acoustic sensing applications, for example, we don't need fast acquisition or high resolution, and therefore can use standard fibers. The same goes for static structural health monitoring applications, where the high resolution is typically needed, but the acquisition speed is not a consideration. For dynamic structural health monitoring applications, we use FBGs, but this reduces the spectral efficiency of the telecom link, as we already mentioned, and therefore sensing and data transmission cannot be done in parallel. As for the high-end applications which involve the detection of broadband acoustic signals at high frequency, those require significant structural modifications of the fiber, and therefore currently remain out of reach of standard submarine fiber optic cables. Let's take a peek at some specific applications. Let's start with DAS. While the fiber cables are designed to be as isolated as possible from the environment, some mechanical coupling takes place nonetheless. And this is enough to show some interesting capabilities, such as the detection of seismic activity, maritime traffic monitoring, and other relevant examples, such as mapping of seafloor fault morphology and sediment transportation studies. Besides the parameters of the optical interrogator system, Thus, accuracy also critically depends on the cable type, which determines the acoustic coupling, the installation aspects, and the seafloor topography, which may introduce variations in the apparent velocity estimation. Structural health monitoring is another important application of fiber optic sensors. In our work, we specifically focus on structures made of composite materials. Composite parts with superior strength-to-weight ratio are ubiquitously used in aerospace and shipbuilding industries nowadays. The weight ratio of carbon fiber reinforced polymers in a commercial aircraft or a corvette-sized vessel is typically above 50%. Alongside their superior characteristics, monitoring the structural integrity of these parts is very challenging. For example, there are some critical defects such as fiber matrix debonding and delamination, which are easy to miss. Embedding optical fiber sensors into these structures can address some of these challenges. As you can see in this illustration, a typical composite laminate is composed of carbon fiber reinforced epoxy plies stacked with different orientations, in between which an optical fiber can be embedded without compromising its structural integrity. Furthermore, many other parameters must be taken into consideration during the embedding process. As for example, the choice of fiber coating and adhesive type may affect the strain transfer characteristics and the overall gauge response. Let's take a look at some specific projects we were involved in. One such project was the static load monitoring of UAV composite wings. A polyamide fiber was embedded inside the wing in order to track the strain distribution along the front spar. The UAV undergone controlled ground loading, and the distributed traces of Rayleigh spectra were recorded at each step. The procedure was repeated several times over more than a year. The overlapping stray curves indicate that the structural behavior of the wing did not change over that period. This monitoring protocol is especially critical during service. In another project, a typical fuselage composite stiffened skin panel was selected for demonstrating the benefits of the high spatial resolution of one of the Rayleigh-based distributed sensing techniques, potentially having a major influence on the panel residual strength. A barely visible damage was introduced to a critical stringer-to-skin joint. After the impact, the panel was compressively loaded up to failure. Already at 140 kN, there were clear signs of local buckling failure in the damaged stringer. This demonstrates the capability of fiber optic sensors to detect critical defects, which cannot be detected by other means. To demonstrate the capability of fiber sensors to also monitor dynamic flight parameters, 54 FPGs were embedded in the wing and tail booms of a UAV, enabling accurate tracking of both the vibration signatures and the actual loading conditions of these components. Flight data obtained by an airworthy FPG interrogator during flight test and normal UAV operational missions was recorded and analyzed so that normal structural behavior could be identified and tracked. Based on the data obtained, it is now possible to track the actual load spectra of both the booms and the wing during each flight, with emphasis on the landing impact vibration signatures. The data also showed good correlation with speed and altitude sensors readings and flight maneuvers. Monitoring potential damage to a propeller during service presents a substantial challenge to traditional SHM tools. To demonstrate the prospects of fiber optic sensors for monitoring rotary systems, 8 FPGs were embedded in a composite propeller, 4 in each blade. Here you see me using an electric hand drill to rotate the propeller at approximately 50 RPM. A commercial FPG interrogator has successfully tracked the spectral peaks during propeller rotation. Okay, now we're moving to the next part of the talk, Let us now see if we can gain something by monitoring the mechanical properties of the medium. But how can we probe the mechanical properties of micro and nanoscale optical waveguides? A spoiler, we also use light. Let's first explore the mechanisms of optical stimulation of elastic waves. In standard optical fibers, the dominant mechanism through which light can be used to generate pressure is electrostriction. In the electrics, electrostrictive force arises when the matter is exposed to an electric field. Its magnitude is proportional to the gradient of the electrical energy. If we strictly consider stimulation within standard fibers, only the first term here has significant contribution. Otherwise, if the dielectric constant is not homogeneous, its gradient should be considered as well. The exerted force, in turn, perturbs the material density. The evolution of this mechanical disturbance is governed by the acoustic wave equation, whose driving force, in our case, is provided by the optical fields through electrostriction. There are other ways to optically generate elastic waves. For example, through photothermoelastic effect, where the sound waves are driven by the absorption and subsequent thermalization of the optical energy, leading to temperature enhanced to density variations within the medium. Optical fibers are famous for their extremely high transparency. Therefore, this effect is negligible. However, we employ this mechanism in integrated devices, as we will show further in the presentation. There is also the radiation pressure effect, which kicks in sub-wavelength scales, therefore is irrelevant in our geometries. A complementary effect to optical stimulation of elastic waves is the diffraction of light by sound waves. The dominant physical mechanism in optical fibers is photoelasticity. Through photoelasticity, the mechanical strain induces perturbation in the dielectric constant of the medium. For the case of amorphous materials, such as silica, this tensor equation reduces to a simple proportionality relation, which is captured by the coefficient gamma. The additional nonlinear polarization drives the optical wave equation, as long as phase matching conditions, which we will shortly explore, are satisfied. The effect of moving boundaries associated with radiation pressure is also negligible in fiber geometries. Since optical fibers support only two directions of optical propagation, forward and backward, let's first consider the case of backward scattering. In this geometry, two counter-propagating optical waves, pump and probe, create a moving interference pattern, which is in turn transduced into an acoustic wave via electrostriction. The lower frequency probe wave is amplified in the process, while the higher frequency pump is attenuated. Two principal factors determine the strength of the acousto-optic interaction. The first one is phase matching. We can simply explain phase matching by using a dispersion diagram. Here we see how the two optical waves and one acoustic wave interact while conserving energy and momentum. Please note that the frequency difference between the two optical waves is proportional to the acoustic velocity in the fiber, which depends on its mechanical properties. Another important factor for efficient interaction is the spatial overlap. This very physically intuitive statement is mathematically manifested through the overlap integral formalism. In step index fibers, we can apply the plane wave approximation for both wave phenomena. As a result, the integral is reduced to an overlap integral over the transverse mode profiles. We use the term stimulated Brillouin scattering to denote the positive feedback that results in self-amplification of both the optical probe and the acoustic fields, which grow exponentially along the waveguide. The natural Brillouin limit in a silica fiber is 30 MHz wide, and it depends on the intrinsic acoustic dissipation in the material. When the pump pulse is shorter than a few meters, the gain spectrum broadens and the effective gain is reduced. The most used sensing technique employing the backward SBS effect is called Brillouin optical time domain analysis. The probe wave is amplified by the counter-propagating pump pulses. The position is determined by the time of flight of the pump pulse. The probe frequency is being scanned, and the strongest amplification occurs when the frequency difference is equal to the local Brillouin frequency shift, which in turn depends on strain. Due to the gain spectrum broadening that we mentioned above, the spatial resolution of this method is practically limited to 1 meter. We can overcome this hurdle by separating the creation of the acoustic wave from its interrogation. For simplicity, we will use a polarization maintaining fiber to explain the principle. Here, the acoustic wave is stimulated by two continuous optical pumps that are polarized along the fiber's flow axis. An orthogonally polarized probe is partially reflected by this moving grating. This is why this method is referred to as Brillouin dynamic grating. The spatial resolution is determined by the probe pulse width, and the accuracy of the strain measurement is in principle preserved by the natural Brillouin liveness. The spatial overlap considerations are the same as in backward SBS, and the matching of modal phase velocity is now satisfied as follows. Despite its advantages due to the time it takes to complete the full frequency scanning cycle, this sensing technique is still relatively slow. In order to increase the scan rate, we first have to solve the BDG equations. We start with 4 optical and 1 acoustic wave equation, including the electrorestrictive driving force and nonlinear polarization, and make the following approximations. We make the slowly varying envelope approximation. We assume short interaction lengths, steady state conditions, and pumps depletion and amplification. We arrived at the coupled equations for the probe wave and the reflected probe wave. These are also the same exact equations that describe the reflection from a fiber Bragg grating. If we further assume weak coupling conditions, we find an analytical expression for the BDG reflection spectrum as a function of detuning from Brillouin frequency and detuning from probe reflection resonance frequency. We immediately recognize the two meaningful terms, the Lorentzian-shaped Brillouin gain spectrum and the reflection spectrum of a weak FBG of length L. These two terms also differently respond to external perturbations. When the fiber is stretched or compressed, the probe reflectivity changes. Thus, a smart selection of the working point will translate strain changes to reflectivity changes, as we saw in the case of an FBG. Here we see an application example where damage detection at arbitrary location along the fiber under dynamic conditions is of specific interest. You can see here that the strain profile is different at a certain location because of the defect we intentionally introduced. The measurements were performed while the beam was swinging back and forth. Since we have already linearized the equations for probe propagation, we can use pulse compression techniques to enhance the sensitivity of our system, as we did in the case of elastic scattering. We first derived the BDG reflection equivalent of an impulse response, which turned out to be complex valued, having a distance-dependent magnitude and phase along the BDG. Therefore, interference between reflections from different elements of the coded waveform is expected to take place in our system, and coherent detection is required for proper decoding. During the experiment, a 2 centimeter long section of the fiber under test was periodically stretched by a mechanical shaker driven by an electrical sine wave function generator at 10 kHz. This produced periodic strain in the fiber with an amplitude of approximately 1 microstrain, and the recorded noise level were the equivalent of 10 nanostrains per square root hertz. We also demonstrated a BDG-based sensing method that showed enhanced tolerance to laser power fluctuations and fiber band losses. This was achieved by generating a standing acoustic wave in the fiber. The strain information was then encoded in the radio frequency phase of the beating of the two probe tones. We performed both static and dynamic experiments and were able to achieve similar noise levels as in the case of intensity-based BDG interrogation. What happens, however, if the information you want to sense resides outside the fiber cladding boundary or the jacket? Let us now introduce the interaction between guided optical and radial acoustic waves in the fiber. We know that fibers guide light. Well, the element of surprise is already lost by now, but fiber structure also guide acoustic waves. For the case where there is no plastic jacket covering the fiber, the acoustic waveguide is simply defined by the cladding boundary. There exists a rich zoology of elastic waves. We will limit our discussion to radial nodes. As before, the strength of the acousto-optic interaction first depends on phase matching. Here we consider the case of forward scattering. Please note that we are not concerned with phase matching condition in transverse direction, since the solution of the acoustic wave equation takes the form of a standing wave. If we look at the axial dispersion curves of radial acoustic modes, we can identify the crossings at which acoustic axial phase velocity equals that of the optical mode. These discrete modes are the only ones that satisfy the phase matching condition for forward scattering. Therefore, an acoustic mode can be stimulated by a pair of properly detuned co-propagating optical waves, and the same acoustic mode can also be used to couple between these optical tones. The second factor for efficient interaction is the spatial overlap. The electrorestrictive driving force has to overlap with the displacement profile to obtain efficient acoustic stimulation. And the refractive index perturbation has to overlap with the optical mode to obtain efficient scattering for the optical wave. In this example, you can see how two optically isolated cores of a multi-core fiber can exchange information through acoustics. Unlike the backward SBS case, the net result of the guided acoustic wave Brillouin scattering interaction is phase modulation. The strength of the GAWBS interaction scales with length and pump power, and its spectrum is the imprint of the acoustic mode spectrum. The first observation of spontaneous Brillouin scattering from thermally excited radial modes in a silica fiber was reported by Robert Shelby in 1985. In our system, we do it slightly different. We send an intense laser pulse into the Sagnac interferometer. The pulse excites a wave packet of guided acoustic modes through electrorestriction. The phase-matched co-propagating probe wave picks up the photoelastic phase modulation induced by the acoustic wave and interferes with a counter-propagating probe wave, which remains unaffected. This way, the phase modulation is converted into intensity modulation and detected using direct detection. But why using the GAWBS for sensing? How is it different from backward SBS? Backward SBS measures conditions within the core, such as temperature, strain, and vibrations. Traditionally, to measure conditions outside the core, non-standard fiber geometries or materials are used, or the structure of the standard fiber is significantly modified. The question is, can we analyze the properties of a substance surrounding a standard optical fiber? The problem is that light is confined to the 8-micron core, and the analyte is outside the 125-micron cladding. There is no physical overlap. For this reason, we want to use the guided radial modes that span the entire cladding cross-section and reach its outer boundary. What do the analyte properties modify in the GAWBS spectrum? The modal decay rate of radial modes also depends on internal dissipations in the glass. But unlike in the backward SBS case, the dominant decay mechanism is the outward radiation of acoustic waves at the boundary. Therefore, the mechanical impedance of surrounding medium effectively determines the modal decay rate. Here you see a simulation of a bare fiber in air. The acoustic wave packet is generated in the core, propagates outwards, and gets entirely reflected at the boundary. But when it is placed in water, it is reflected only partially, and part of the energy radiates outwards. We use the sensing principle to measure the mechanical impedance of aqueous solution with different levels of salinity. We could successfully resolve salt-weight ratios of several percents. For reference, state-of-the-art conductivity temperature depth sensor can be 10 times more sensitive, but it is expensive and bulky. So far, we have showed integrated sensing capabilities. But can we do distributed analysis? The problem is that guided acoustic waves induce forward scattering, which cannot be mapped using time of flight. We have overcome this major difficulty using the following protocol. We are sending two co-propagating tones down the fiber. When on resonance, they stimulate the guided acoustic mode and exchange energy in the process. The gain spectra are extracted from local power levels using Rayleigh-backscattering. How about that sensing techniques fusion? In this work, we have demonstrated distributed mechanical impedance sensing with 100-meter spatial resolution. What about point sensing? For this, we use the multi-core fiber and optically stimulated radial acoustic mode in the center core. It propagated outwards and generated photoelastic perturbations in all outer cores. These perturbations were monitored with fiber Bragg grating sensors inscribed in the outer cores. Here as well, the separation of the creation of the acoustic wave from its interrogation allowed for optical background-free measurements with high sensitivity. The last form of acousto-optic interaction that I want to discuss is the interaction between guided optical modes and surface acoustic waves. Before I show you our work, I will give you a brief overview on integrated waveguides, opto-mechanics. In principle, standard silicon photonic materials support strong electrorestrictive and photoelastic effects. Unfortunately, standard integrated photonic waveguides do not guide sound. Elastic waves driven in the high stiffness silicon waveguide rapidly radiate into the underlying silica substrate. Two principal mitigation pathways are considered by the opto-mechanics community. The first one is removing the substrate and leaving the optically guiding core layer suspended by tethers. These membranes support guided elastic waves with shear and flexural character, some of which can mediate transfer of energy between optical modes. An alternative solution is to replace the silicon with soft chalcogenide glass, which has high refractive index and relatively low stiffness, thus allowing the confinement of both optical and elastic waves by total internal reflection. The second approach is the introduction of surface acoustic waves into photonic integrated circuits. The traditional technique relies on electrical excitation of surface waves in optical-grade piezoelectrics. These materials platforms have very large electromechanical transduction efficiency, and also support optical waveguiding. The optomechanical coupling is designed to take place in the waveguide core, where the radio frequency information carried by the surface acoustic wave is imprinted on the optical carrier. We took this principle one step further and showed in a recent publication that surface acoustic waves can also be generated in standard silicon device layer via photothermal excitation. One last important note, in both of these SAW devices, the generation of acoustic waves and optical scattering processes do not spatially overlap. Therefore, the system on the right lack the positive feedback needed for self-amplification of both the optical probe and the acoustic fields. The systems on the left, on the other hand, do support stimulated Brillouin scattering similar to optical fibers. In our device, high-frequency surface acoustic waves were stimulated through absorption of modulated pump light in periodic metallic patterns and their subsequent thermoelastic expansion and contraction. The resulting strain pattern was transferred to the underlying silicon device layer, which supported surface-guided acoustic modes, as shown here in this numeric simulation. The acoustic waves were detected via photoelastic modulation of an optical probe, which propagated in a standard silicon racetrack resonator. To monitor the periodic shift in the transmission spectrum of the resonator, the probe wave was tuned to its slope, as we already saw many times throughout this presentation. Some of the devices we fabricated could generate and detect surface acoustic wave frequencies as high as 8 GHz. In a subsequent experiment, the spectroscopic capabilities of this sensing protocol were demonstrated. A 57 nanometer thick alumina layer was deposited in the surface wave path. And as a result, a spectral shift in the device transfer function was observed, which corresponded to a change of 20 meters per second in the acoustic velocity. The sensitivity of the device to SAW velocity changes was estimated at 500 ppm. Okay, so here will be a good place to stop. Although I wanted to discuss additional relevant sensing protocols, such as hydrostatic pressure sensors, ionizing radiation sensors, and shape sensors. I also wanted to discuss the advanced methods for coherent control of light and sound propagation, which is an interesting and important subject in its own right. And also show prospects for underwater detection and ranging based on light and sound interaction. Well, I guess we'll have to schedule another seminar, right? And now I want to thank you and all the wonderful people I had the privilege to work with during the years. And I want to thank you for your attention. Okay, thank you.
Thank you very much.
Thank you, Arik.